nothing. A blank sheet is actually quite amazing. Like, it can be so many different things while also just being nothing. Like, let's say I turn it like this. You may get that horror reaction from like, oh shit, I have to start this essay with only 1 hour on the deadline. Whereas if I then turn it like that, it may give you that enthusiasm of, oh yeah, let's go draw something fun. Because you can put so many different things on here, this one empty paper can become so much more valuable than just this one single sheet of wood stuff. Like, will this become the summons for that money you've borrowed? Or will it become the winning lottery ticket that will just change your life? Just like paper, computer screens can also show you many different things. And whereas for paper you use like paint and brushes to create something on it, like for instance, hello world, on the computer you use special messages that you send to the computer to create something on there as well. This is what we call programming. The biggest difference between the paper and the screen, however, is that paper can only show you something. So take this calculator right here, this will never ever solve this equation right here. However, because the display has an entire computer behind it, which can do something, I can create something like this calculator right here, which actually works and will give me a real answer. In other words, with this computer screen, I can build actual tools. This is one of the things that makes programming so powerful. It doesn't just allow you to create most of anything on the screen, but it also allows you to make tools which you can then again use to make even better things occur on your screen. And because all these files are so easily shared with people around you, if you make something good, it can have a big impact on the world very fast. Now that sounds nice and all, however, where I can pop by the corner store to get myself some paint and some brushes, like, where do I get myself a box of programming to do something on here? Well, you can't. Sorry, but it's true. That's because programming is a skill, like drawing or painting, which, as of now, you can't put in a box just yet. So to understand the skill, let's start from the very basics of what it means and how it works. In the last video about software, we spoke about how computers are electrical devices that can do a whole bunch of things, but only if we make the right connections. By making a bunch of smaller connections within a computer, we can combine simple actions to do much more complex things, kinda like a recipe, which is what we call a program. And the act of making these programs is what we call programming. In the earliest computers, programming was done by actually disconnecting and reconnecting the wires in specific locations, allowing the electricity to flow where we wanted it to flow. Later on, what they did was take all these connections and put them in one single location, such that you could push through a card with holes allowing electricity and no holes allowing no electricity. As such, we were now able to run the same program by just stamping some holes in this paper. What's really interesting though is that if you look closely to this paper, what we find is that we've actually made a code for connecting these wires right here. Now we can write down this code by saying that any place where there's a hole has a value of 1, because that's where electricity can flow, and any place where there isn't a hole has a value of 0, because no electricity can flow. So that would mean that the code for just these 2 rows for the action of like turning on light 1 and then light 2 would be 0, 1, for turning on light 1, and then 1, 0 for turning on light 2. Now what's crazy cool here is that just like in the last video where we showed that the connecting of wires like this that we do here was actually the way that they connected wires on the earliest computers, well, this code right here that we've made on this little card with 0, 1 standing for 1 and 1, 0 standing for 2, that's also an actual code. It's called binary, and it's what all these computers run on. Now while it's really cool to know that 0, 1 is 1 and 1, 0 is 2 in computer language, this is only really useful if you're only turning on light 1 and light 2. But let's say that you want to light up a display like the one you're watching this video on right now. Then you'll most likely need 1920 by 1080 little lights, which are going to be 2 million lights, which, it's gonna be kinda hard to fit all these holes on this piece of paper to run all these 2 million lights. This is where we're going to need a little bit of help from the processor, also known as the brains of a computer. This is the thing that we send all of our input to and then does all the calculations to make the things happen that we want to have happen. To show you how we can work with a processor, here I've made like a smaller, older processor called a microprocessor, which used to be used in things like the Atari 2600 and the NES. Now, as you can see, this processor right here has like a bunch of little feet on the side, which kind of make it look like a big ass centipede. However, these feet aren't feet, they're actually pins, which serve as connection ports. Connection ports are basically just places where you can connect something to and then send input to or receive output from. As an example, if you take your phone, on the bottom there's a connection port where you can send in power, and on top there's a connection port where you can receive audio. Similarly, all these pins right here on the processor are different ports for different little things. I think the most simple one to understand right here is going to be the ground and the 5-volt, which are like the 2 pins you need to power the chip on. Now that's very similar to a light bulb right here, which also has like the longer prong right here for 5-volt and the shorter prong for ground. If you can see that, if it doesn't move around too much. But yeah, just like how supplying power to these 2 pins on the light bulb turns it on, in the same way supplying power to these 2 pins on the processor also turns it on. However, this processor doesn't just turn on and then we're happy with it, like we are with the light. We also need to send data to it and receive data from it. That's what we do on these 8 data pins. Right here we can send information and receive information as well. Let's see how we can actually communicate with this processor to make it calculate the hardest sum known to mankind. 1 plus 1. So if we want to calculate 1 plus 1, what we want to do here with the processor is we want to tell it some things. Like first we want to tell it a 1, we want to give it a 1 here on the data pins. Then we also want to give it another 1, and then hopefully it will give us the 2 right back. However, we need to keep one thing in mind, and that is that this processor can do a whole bunch of things, so we can't just give it a 1 and then expect it to know what to do with it. We need to give it some instructions what to do with the numbers that it receives. So what we need is the following. First of all, we need to tell it that we want it to load in our number 1. Then what we want it to do is we want it to add another 1. And then what we want to do is we want it to load whatever is the result of what we've done before. Now it's very likely that you've already noticed one small tiny little thing, and that is that this right here is basically the same as this right here. However, this is super hard to understand. Like, I've looked this up, I have written this out, and I've also painted it right here on the pieces of paper, but still, I would not really be able to tell you that this is 1 plus 1 just by looking at it. Like, this is so much more readable, and this is just gibberish. Sure, we're not working with wires anymore on computers that can get tangled all ways around. However, making this programming digital hasn't really made it that much easier to read than these stamped cards. Like, I don't really know what's going on here. Like, for sure, this works well for the pins on the chip. Like, these are the exact digital signals that we need to send. But I can't read any of this. And if you think that that is somewhat impractical to work with as a human, well, don't worry. It gets even worse, because these things right here are just our wants, which are somewhat understandable. However, these things right here are our instructions that we need to give. Now, these instructions right here are only working for this processor right here. If there is a new processor that comes out, which, let me tell you, happens basically every year, a couple of dozen of them come out, it doesn't mean that this will work on the same chip, because not all the chips are the same. This right here is the exact spot where programming languages come in, which is the programming that most people are used to today. Now, programming languages are basically like a translation layer that take all these ones and zeros that are very hard to follow and make a translation to them for words that we can somewhat understand. To show how this translation works, let's go take like the 1 plus 1 equals 2 as an example. Let's make this thing right here, the things that we communicate to the processor right here, a little bit more readable such that you can actually understand what this here says. I think first of all, what we can do is we can take the 1, which is already quite easy to read since it's just a 1, and let's just make it a number 1. Simple enough. Then we still have these like operation codes, which are just like a whole garbled mess of ones and zeros. Now, if we look very closely, we can find out the load codes are both the same, because first we want to load in the 1, and then we want to load in the 2, like we want to load that to our output. So we can call those things load and load. And then we're left with only one instruction right here, which is add this 1. So this should be an add, so we can just make that add. And as we see right here, right now we have the same set of instructions, load, 1, 1, add 1, and then load the answer. But instead of it being a garbled mess of zeros and ones, it's become load 1, add 1, and load the result. Now, this is something that we can actually read. Like right here, I can actually explain to you in very simple terms that this is what happens with a processor. Now, both sets of instructions mean the same thing, with the big difference being that we can't really understand this one, but we can understand this one more easily. For the computer, the only thing that it needs to do is just translate this to that, which it knows because it knows that load means that, 1 means that, and then it can run the same actions right here. So for the computer, it doesn't make that much of a difference. That's the whole idea behind the programming language. It's a translation layer from the machine code to more human readable code. And just like how previously the ones and zeros that we showed were an actual code called binary, this right here is an actual language called assembly, which is the lowest level programming language, which is the heart of all programming. But then, what does it mean to be the lowest level programming language? Well, let's just do a quick recap of what we have so far. Programming started out by just making connections within the computer by either having electricity or not having electricity, having ones and zeros. In order to do more complex things, we now have processors which can help us to do things that we don't have to do ones and zeros for every single small action. These things can help us calculate and do different more complex things. They are the brains of our computer. And in order to communicate with them, we still use these ones and zeros. However, using these ones and zeros can be very confusing, and a programming language right here is our translation layer between these things. It still means the same thing, however we can write out what we want to happen, and the computer can just equate that to the ones and zeros of the meaning behind that. It basically makes programming more readable because it translates binary to something that we can understand. However, there is still a limitation with this method right here, because what we see right now is that we have translated like the words right here into something that we can read. However, the structure is still the same. If we look at what we humans would use, like 1 + 1 = 2, it basically has a structure of one single sentence. However, with assembly right here, we're still using all these lines here to convey our operations. This is what it means to have a low-level language. It's quite simple, it directly translates the machine language. Whereas what we can also do is like the moment that we start already changing things around, we could also just say like, hey, we're gonna have a language that says x + y = is the same thing as all of this, but then having an x right here, let's have that stand in the right way, and a y right here. If we can do this already, then why can't we do that? And that is what a higher level language is. Of the higher level languages, there are two notable types, which are compiled languages and interpreted languages. Don't worry, I did not forget the R there. Or maybe I did forget it. Anyway, compiled languages are programming languages where you first write your code, like let's say x + y =, and then you translate the entire code into assembly. So you would translate it to this. And then after you've done that entire translation, which is called compiling, then you can run your program. Interpreted languages, on the other hand, don't need to do this translation after you finish writing the program, because they have this interpreter which does it in real time. What that means is that it basically has like this translator, or interpreter, which when you run your code, x + y =, looks at the x and then thinks, okay, x means load x, plus = add y = load. So it does that in real time. Because of this, compiled languages tend to be a lot faster, since you've already done the translation before you're running your program. However, interpreted languages are a lot easier for learning, since you can just kind of like try out your code at any point in time. Since you don't need to compile it, you can just give it a shot and see whether it works. If you want to try out coding, you generally need to install your programming language that you want to use first, and then you need to install a code editor, which is basically this software in which you can just work with your code. An example of this right here is Visual Studio Code. As you can see right here, I have written up some code in Python, which as you can see right here is an interpreted language. So as I've written this code, what I can do is I can just go and press the play button, and then as you can see right here, the code runs. And what we see here is that we just ran the code successfully. It says print 1 + 1, which is the result 2. And that's basically all there is to programming, which I can understand may be a little bit surprising to you, since basically all the actual program that we've done in this video was write out print 1 + 1, but that was just for like showing something off. However, I think it's very important to understand the basics first before you start to get into programming. And that is that we're just trying to send messages to a computer, and the way that you do that is by ones and zeros. But then I don't want you to be surprised to then get into a programming language and find that there is hardly any ones and zeros, but you can just read it. And that's because we can't really read and write in these ones and zeros, so that's why we have these languages, which are these translation layers. However, these translation layers also have some logic to it. That means that you can't just start writing whatever like paragraph you want to have happen, because that doesn't work. So that's just the basics that I want to give you across. Now the specifics, I don't really want to get into with this video. That's because there's a whole bunch of different languages out there, which all work via their own different ways. Kinda in the same way that we have human speaking languages. And just like how we have speaking languages, you don't really have to know all of them. Because if you have just one or two, you can kind of get by. And the more you know, it will be better, but it's not necessary to know all of them by heart. That said though, if you know just one, it should be easier to learn others since you kind of get a feeling for how it works. In that spirit, the language that I would recommend you'd start out with is actually Python, which I've been writing in right here. Python is an interpreted language, so you can kind of like more easily get started with just writing and trying out and testing it. And it's also very readable. It's basically a language that a lot of people get told to start out with, and I think that's a really good recommendation. You can get it right here from like python.org and just download it for your system. And then using a code editor, you can just start out trying to print hello world right here. I can imagine that coding can still seem quite overwhelming, especially when we often see in movies these big lines of codes going at a really fast pace and people typing them as though they know exactly what to say to the computer. However, keep in mind that at the end of the day, code is just a simplified logical translation of the messages that we're sending to our computer. And these messages have a structure to them. So if you can find a good tutorial and just learn step by step how to do small little things, like just printing a single sentence and then moving on with that, I'm pretty sure that you're very easily able to grasp what's going on. This video was really much more about a general idea, and I hope that I get the general idea across and that it's clear to you. But if it's not, feel free to ask in the comments down below. But that's really all there is for today. So thank you all for watching this video, and also thank you so much to everyone who is supporting this channel. For $1 a month, I make extra videos in the form of overtime, which are extra videos which are going to be happening right after this video right here, where this week we are looking at the Raspberry Pi, the actual Raspberry Pi. Like I faked it out once before. Back then we tried to build a computer, but this time we're actually going to be starting this up. This right here is like a little computer which is all about like programming on it, but not just programming on it to make like fun little like computer programs on it. The really cool thing about the Raspberry Pi is that it also has like these little pins, which you can see right here, which can actually do stuff in the real world. Like, remember that little breadboard that I made? Like this thing right here. Like these pins are designed so you can like take a wire and put it right in here and then actually power on these lights through the Raspberry Pi right here. So you can write code and actually have lights light up right here. It's basically bringing it full circle, like taking the computer stuff back to the real world. And I've never really worked with that, and I think it will be so cool. Today was just all about programming, and I've had a fun time. I hope you guys had too, and I'll see you all next time.